Our next talk is called From Origins to Open Source, the journey of DreamWorks Animation's production path tracer, MoonRay. And so I'd like to welcome to the stage Randy Packer from DreamWorks.
Thank you, everybody, for joining. My name is, as you mentioned, my name is Randy Packer. I am Senior Manager at DreamWorks Animation, managing a few teams, including the render and shading team, which are the engineers that built MoonRay, our production path tracer, which I'm going to talk about today. Now, I've done this before, sort of, in front of podiums, and I know myself, so um, the instant that I stand up in front of a podium, all the memory in my head pages out and gets swapped in with complete void. So I'm going to read speaker notes uh, pretty extensively, but they are my own words. They are not marking copy or anything like that. So with that said, let's get started. So here's what we're going to review: an introduction to ray tracing that's suitable for a PhD program. Sorry, I mean succinct enough to fit into our time slot together. I'll introduce MoonRay, the production renderer used for all the feature films at DreamWorks. MoonRay was built on modern computing architecture with the intent to provide interactive scene visualization with the ability to selectively scale compute resources to suit each artist's workflow. We'll look at how MoonRay's development took place, and finally, we will discuss DreamWorks' motivation to open source this technology, which happened earlier this year, along with the journey to get it out the door and what's next. An MCRT renderer tries to emulate real-world light transport as accurately as possible, at least when we want it to. Sometimes we bend the rules to depict very unique and inventive worlds. And I should mention, most of the images that you're going to see in this slide deck were renders from MoonRay. So to give a background refresher for anybody who doesn't know ray tracing, I'm going to describe it in very simple terms here, specifically the naive approach of forward ray tracing, or basically how particle transport works in the real world and how we humans are able to see things. Here we have a simple scene with a light source, some sort of polygon object in a sphere floating in space, and this green happy face that is looking at the scene. First off, our light source emits photons. And since we don't know if a photon is a particle, or a wave, or a field, or all three, let's simplify our approximation and call it none of these things. Let's just pretend it's rays of energies and visualize what those rays are doing. Here we see our light source is emitting rays in all directions. And we'll follow just one of those rays that reaches the surface. Now, the surface isn't smooth, so it's going to reflect light into the environment in multiple directions. One of those directions is towards the eye of our viewer, so they can see the polygon directly. But light will also be bounced towards other objects in the environment, and once it reaches that other object, it will also scatter light based on its surface properties. And one of those directions is towards the eye. But perhaps it's also transparent, and so it will refract light through the object, and some will scatter out the back, but some will also be reflected back again through the object and potentially reach the eye. Now, this is clearly simplified, but it should give you a basic idea. If we wanted to simulate this on a computer, we need to start tracing umpteen billions of rays from the light source. Umpteen is a technical term that managers like myself like to use. However, only a vanishingly small percentage of light rays would ever reach our viewer's eye, so we'd be wasting an awful lot of computation. So in computer graphics, we turn this around. We simulate this with backward ray tracing and turn the problem around. In backward ray tracing, or simply what we call ray tracing, we put a grid of pixels in front of the eye and trace rays into the scene to see if they eventually hit any light sources. In this way, we immediately eliminate all the light rays that never reach the eye, so we've already optimized our task. Then for each pixel, we trace a number of rays. Now, if we only traced one ray per pixel, you would see a very blocky version of the scene. But as you trace more rays per pixel, you get a better approximation of the final correct result, and thus it looks smoother. That's a side note. For now, let's concentrate on just one ray at a time, since the process is the same for each one. Let's start with this pixel, and we see that the ray intersects the sphere, and it will send out refraction rays. At the sphere's surface, we use importance sampling to pick good directions to sample in the scene, and we shoot rays out in those directions. We achieve this because we know which directions a light emits the most energy and which directions a surface reflects the most energy, and instead of shooting rays out in all directions equally and wasting compute, we can choose from those directions and combine the probabilities using what we call multiple importance sampling. Yes, one ray from the eye fractures into multiple rays as it encounters each surface. And some of its surface rays will hit other objects, and other rays from the scene will also hit those objects, but at different angles and thus different sample patterns. And we keep this up until eventually something finds a light shining on it, and we return the color of a pixel. And that's what a renderer does. It paints a pixel. Repeat this over billions of rays, and an image comes out at the end. So where does a path tracing renderer like MoonRay actually fit into the feature film production pipeline at DreamWorks? Here you can see various departments involved in the process, and while not always strictly linear, there is a certain flow to upstream departments handing over to downstream departments. Now clearly, there's one spot indicated here and with a green arrow that absolutely needs to be there, which is rendering or capturing all the final frames that make up our movies. However, rendering happens in many departments during the course of the show as artists iterate and refine their work over the course of that production. So let's continue. MoonRay is our high-end production rendering system. It replaced Moonlight, a deep frame buffer micropolygon rasterization system. We were by no means the first major studio to make the change from micropolygon rendering to path tracing, but we learned a lot from those who went before, and we approached the problem with a ground-up rewrite. As I mentioned previously, it is a Monte Carlo path tracer, or MCRT for short, 100% ray traced, it's easy to use, and provides artists with fast iterations. It can be integrated into a wide variety of digital content creation tools, or DCC tools for short, such as Houdini, Maya, Katana, Blender, an in-house lighting tool, etc., with an appropriate plugin or as a USD Hydra rendered delegate. And I'm going to explain that last part a little bit later. MoonRay's algorithm is best described as backward path tracing with next event estimation and multiple importance sampling. Internally, we provide MoonRay as a service to our clients or our shows via our in-house cloud framework, which we call Eris. Not only does this simplify application integration, but it also allows MoonRay to take advantage of massive machine-scale distributed rendering. So MoonRay can render images that are photoreal. The glass on the left is rendered, the one on the right is real. A coral dragon, for instance, this asset came from Shrek. We made it translucent in this image. Or we can render the more fantastical, such as glittery dancing trolls. Shaders are plugins to the renderer that describe lights, materials, geometry, etc. Moonshine is a package of capable production shaders that are included with the open source MoonRay repository. Here we have a wireframe mesh of our version of the standard Shaderball 3D model. We've open sourced this model on the Open MoonRay website. We can shade it in a plastic diffuse material in multiple colors. We can make it glossy or like glittery car paint, iridescent, scratched and aged bronze, translucent. We can layer materials on top of each other, like this kind of frightening skin in copper, or water on plastic. Or we can simply flood the room, or create something cool for Halloween. We wrote MoonRay from scratch, leveraging state-of-the-art open source components where appropriate. No studio legacy code was used. The architecture is cleanly divided across 3 different APIs. The rendering API for clients to initiate rendering, the shading API for development of pluggable shaders or materials, and the procedural API for the development of geometry generators. We use best-in-class open source libraries. So not only are we open source, but we also use a lot of open source in the product. Embry is our ray intersection engine, initially developed by Intel for MoonRay and in collaboration with us, and then later open sourced by Intel. We use OpenImageIO to generically handle different image file formats. It was written by a developer from Pixar, then NVIDIA, and then Sony when he got tired of writing the same library at every company he went to. OpenSubdiv is an open source geometry library contributed by Pixar with major improvements from DreamWorks. OpenColorIO is an open source color management library contributed by Sony with an emphasis on visual effects in computer animation. OpenEXR is a professional grade image storage format in wide use in the motion picture industry. It was developed and contributed by Industrial Light and Magic. OpenUSD is an open source scene description specification developed by Pixar and recently founded in alliance with Adobe, Apple, Autodesk, and NVIDIA to promote the standardization and evolution of the technology. And OpenVDB is a volumetric representational data format and set of tools that we developed and open sourced at DreamWorks that has transformed movies. In fact, if you have seen a VFX movie or a TV show with explosions, fire, water, or fog since 2015, then you have seen OpenVDB in action. It swept through our industry so rapidly that 4 of our developers won a SciTech Academy Award. These are the same people who do the Oscars for it the very next year after we released it. That is tremendously fast for a SciTech award that generally waits years to ensure that there is a positive impact in the industry. And we are very proud to have spearheaded that. So, all renderers have personalities. Keeping all the lanes, ... is our mantra and our personality, and a key aspect of our vectorized architecture. This is our guiding principle for development. Our goal was to achieve scalability up to real-time rendering and leveraging all the available hardware. The need to trace and shade billions of rays implied thin interfaces and no data structure redundancy. We embraced data-oriented design, which is a methodology that first grew in the games industry, but we applied it with great success in MoonRay. Compared to vectorization, which I'll discuss in a moment, multi-threading is quite straightforward. First, we divide the frame into 8x8 tiles. Idle threads pull the next tile from the queue and begin work. And we have some techniques to ensure that the artist gets a rough pixelated image quickly and that computation proceeds without any locking, so we avoid Amdahl's law of diminishing returns when coordination is required during multi-threading. And here are the results. Exactly what we like to see, all threads fully loaded. Let's talk about vectorization. This is the process of setting up blocks of computation where the same instructions can be executed simultaneously on different chips, or SIMD as it's called in the industry. Modern chips provide a large number of vector lanes. MoonRay ray data flows in and out of queues that prepares the data to be bundled into the SIMD vector pipeline. On AVX2 chipsets, for instance, we can perform 8 operations for the price of 1. Let's look at some results. Here's Astrid from How to Train Your Dragon in a test T-pose. There's a lot of fur and hair in this scene, and the biggest block of time at the bottom in blue, the incoherent rays, is spent inside of Embry, Intel's open source intersection library that we developed in conjunction with and for MoonRay. Since Embry is already well vectorized in both our scalar and vectorized code paths, we don't expect to see an improvement in this area, nor do we see any improvement. However, we do observe significant gains in shading, texturing, and integration, and despite the overhead for vectorizing the scene, we see a good result with about a 37% performance improvement overall. Most commercial ray tracers are structured such that the digital content creation tool, DCC, like Maya, Houdini, Blender, etc., run the render inside of their own process. This makes the process quite large, and if either the renderer or the application have a problem, both end up crashing. As I mentioned, Eris is a thin layer API for rendering. The artist can start MoonRay as a separate process on the same computer, or they can run it on a separate computer. This enables the artist to use a lighter weight computer with a beefier backend for rendering. Or, for even better performance, you can distribute the rendering onto multiple remote blades to accelerate the interactive display for the artist. Thanks to not locking, the speedup obtained is linear with the amount of computation added, and this is robust to a failure of a node. If a remote computers fail for any reason, the render continues, but at just that percentage slower. This architecture, while seemingly simple, has produced linear speedups on clusters of up to 96 hosts. That's the most we've tested because it's the most the execs authorized for testing purposes. And you can see at 40 hosts, we show 40 times speed up over a single host. And just to really reinforce the definition of linear here, a test from our Glendale location to 96 blades in the Azure West US region, we saw 96 times speed up over a single host. Each host had 128 gigabytes of memory, 64 hyper-threaded cores. This demonstrates the commitment we've had to never locking or waiting on the results of another computer or computation. So I mentioned Hydra render delegate before. So Pixar had released a scene description format called USD for Universal Scene Description, which contains a definition for a Hydra render delegate that defines a common interface for renderers. You can think of this a little bit like a PostScript interface. You've got many applications in the world that can write a PostScript file, and you've got many printers that can accept a PostScript file and print on it. In a similar way, you can think of Hydra as a standard interface that eases the integration of renderers into artist tools. MoonRay supports the standard features you would expect in a production renderer, such as the ability to use light path expressions to select and isolate certain light paths in order to do post-rendering compositing operations. You can think of this as something like regular expressions for light. For example, we can use an LPE to perhaps distort the glossy reflection of an object to make it look otherworldly. AOVs, or arbitrary output variables, allow direct visualization of key material properties to discover anomalies or inconsistencies across characters and environments in order to ensure that we have well-behaved materials before the full production lighting phase begins. We can use these light path expressions in AOVs as layers to input into pluggable display filters that take those shader outputs and do operations like cartoony post-processing and more. We can art direct many different looks and styles with MoonRay. In this slide, I like the dust on a translucent ball there, so that's why I put it in there. MoonRay is actively developed, battle-tested, and in use at DreamWorks for our recent and upcoming feature films, such as Trolls Band Together, which is out in theaters right now. We range between 92 and 154 million core hours for a DreamWorks feature. As we continue to develop MoonRay's capabilities to support the ever-growing needs of our feature film productions, we are definitely excited to see how its open sourcing can make it even stronger. And this is just to give you an idea of the kind of data that we render. It's a lot. And the complexity of the scenes that we render. I'm amazed at the attention to detail given to every single frame of our movies, particularly when I sit in on dailies and listen to production leads and department heads give notes on such exacting and seemingly small details that would be difficult to see at 24 frames a second. However, it is exactly these kinds of details that, although an individual item on screen for, say, less than a second may not uniquely stand out to the viewer, they absolutely add to the extraordinarily rich and comprehensive worlds that we create. It's what makes our movies visually memorable and cumulatively add to the richness of the experience. Let's continue on. We made an initial proof of concept in 2012 as a project called Orchid. Our goals with this project were to demonstrate the relative ease with which we could assemble a functional MCRT core renderer, evaluate Intel's Embry as the underlying geometry ray tracing platform, identify areas in which work would be required in order to deliver a production solution, and do all of this quickly and without impacting other studio priorities and schedules. Pardon me. Here we're seeing an early demonstration of the ORCID proof of concept, focusing on fast time to first pixel for lighting changes as the light source is moved around the scene and radiance values are modified. This demonstrates the ease an artist has to make fast iterations on the scene. In the second part, we see the adjustment of material properties on a marble by decreasing its roughness and seeing how the light contribution changes. So what was next? Design it as a new renderer, implement what was missing in Embry, write the scene procedural shader and sampling APIs, and plan for an open source product. Actually, I wasn't there at the time, but I read that in the deck. They were planning way back then for an open source product. To that end, we started an experiment in about 2013 to produce an interactive renderer for product design, not for animated movies, but for product design with an effort that we called Nova. Here's an early example demonstrating hair and makeup preview for a cosmetic company. While you might think you've seen faster displays in video games, this simulation does subsurface scattering of light under the skin based on the thickness of skin and pockets of fat. There is multiple scattering in the hair to emulate accurate hair lighting. And all humans have hair fuzz on their skin, and this model includes that. It's a sophisticated model. MoonRay and Nova did many product designs, such as simulated fabric and drapery designs here in situ in a room environment, and we can change those draperies. The Nova initiative also drove the development of Eris for distributed multi-machine computation and integrated MoonRay well to add linear scale for rendering as the number of hosts is added to the computation. In this video, we are rendering Poppy from the movie Trolls on 14 hosts, each with 40 cores for a total of 560 cores. Each host had a Xeon 2.8 gigahertz CPU. Now this is very fast with these mini curves. It's very fast to render to that level. Our VFX supervisor on How to Train Your Dragon: The Hidden World saw the results achieved with Nova, and in early 2018 made an impassioned plea for MCRT. And you know rhyming rules must be followed. The following is a test scene that he set up to convince the execs that he could use it on the movie. He wanted to be sure that we knew, all of us here in the room and online, that we knew that this is only a test and is not the final surfacing, lighting, and rigging that was actually used in the movie. I can't really tell, honestly, and you likely won't either, but we need to point out this is just a test. So, this convinced the execs that the look could be achieved. Thank you. Yeah, that looks very beautiful. This convinced the execs that the look could be achieved with MoonRay and could handle the complexity of dense foliage, shading complexity, the ease of lighting setup, and the speed of rendering. His plea for MCRT was greenlit. Thank you very much. I was fortunate to sit in the dailies room when the VFX supervisor made his pitch to the execs, and the mood was electric. It was such a passionate pitch that this story, the world, and the characters in it deserved the richness that MoonRay would bring to the look of the film, and he was right. It's a gorgeous and beautiful film full of artistry. Of course, now that this particular technology was sold, the show still needed to get made, and we were on a deadline with a fixed release date for the movie. We had a lot of work to add some required features into the renderer, as well as get it running across the show's entire pipeline so that artists could use it. Our strategy was simple. We deferred anything and everything which had a workaround to achieve the show's look, and we focused exclusively at first on those things which had absolutely no workaround. For instance, we needed to support crowds and volumes, such as fire. In fact, at the time that we were greenlit to be used on the movie, we did not have a volumes integrator at all, and one of our engineers did brilliant work to develop one in time for the full production pipeline to ramp up. Lots of caffeinated drinks and metal music were in that delivery. He loved it. There's nothing like a cool challenge to meet. Many people may think that How to Train Your Dragon: The Hidden World is about base jumping Vikings, or the evolving relationship between a boy and his dragon, or the loss of loved ones, or the depiction of disability and the characters that thrive nonetheless. And these are all true. The movie could have also been titled, in my opinion, How to Break Your Renderer, as it is also true that this is a movie about some of the hardest rendering challenges to overcome. Many scenes with indirect light sources, depth of field, volumes of all sorts, clouds, fog, fire, water, and smoke. This is one moody film. The acclaimed cinematographer Roger Deakins was a visual consultant, and it shows. Although The Hidden World was the first feature rendered with MoonRay, and while its production pipeline was ramping up, we also rendered a short, Bilby, on MoonRay to test what was working and what we needed to improve. The short was first released at the Annecy Film Festival in 2018 and received a Jury's Choice Award at that year's SIGGRAPH conference. Now today, a special treat for everybody in attendance and online, as there isn't a session directly after this one, I will present, after my presentation is done and Q&A is done, I will present the Bilby short in its entirety at the end. It's only 8 minutes long. You feel free to, go take a break or watch it and then take a break. I do think it's worth sticking around to watch. It's a nice movie. Let's continue on. So, MoonRay sounds great. What an amazing technology. So why on earth did we open source it? Let's start with our timeline. We got the green light to open source in January of 2022, though we've been working on pitching the idea internally with the execs for a year and a half prior to that. Once we had the green light, we moved pretty quickly to initiate and start the project in March with an ambitious goal to release it by the end of the year. We reorganized our roadmap to carve out some activities in the project, which I'll discuss in the next slide, and the team got busier than they already were. We decided to announce our intent to open source at SIGGRAPH in August of 2022. That generated significant interest in the graphics community, and we gave an impromptu presentation at the co-located open source days hosted by the Academy Software Foundation at the same time. We invited people to sign up for news and beta testing, and a bit more than 4,000 people did so. The team continued working on getting everything ready, along with doing our normal development for our feature productions. However, we missed our internally set deadline for an end-of-year release. Basically, we knew by mid-November we weren't going to make it at the quality we felt we needed for the initial launch, so we broke the news, but committed ourselves to a Q1 launch in 2023. Also, we wanted to have Christmas with our families, right? And that's just what we did. Open MoonRay was launched live on March 15th, and we made it. Since then, we've made an additional 4 update releases. The latest, to my colleagues back in Los Angeles, was yesterday, but for us here in Riga, this was today. we just released our latest update today. So this is just a bit shy of a new release every couple of months that we're doing. We focused on a few core items for getting to open source. Of these, the 2 largest by far were replacing our internal build system of sconnes and standing up a robust documentation site. So I just mentioned we replaced our build system from sconnes with CMake. We extricated the code base from our internal library dependencies. We did some minor code cleanup and refactoring, and we stood up a brand new public documentation website. Our goal throughout all of this was to provide a system and documentation as thorough as possible, given our time deadline for first launch that we knew would not be perfect or final, but good enough so that people would want to come back after our first visit. So we asked ourselves, if we were searching for an open source project, what would we minimally want to see? I did mention that we're updating our repos approximately every 2 months. So far, this has been a good cadence for us as we develop new features for our productions and for us to stage our release and do all regression tests, scans for FOSS hits, et cetera, like that. We've been open source for a bit over 6 months now. So what else has been going on since then? Well, for starters, a ton of documentation additions and updates. We're nearly through our core set of documentation taken from a variety of wiki pages of questionable timeliness, to be honest, and improved it all, adding videos and images to show off the features as best as we can. This new documentation site has actually become our go-to for all things MoonRay internally with our productions. What's coming up next? In the near term, we have a strong focus on updating our pipeline and tools for the next version of the VFX reference platform. Many studios are attuned to the VFX reference platform as it specifies specific versions of softwares that are known to be compatible with each other. This next feature I actually had is coming up soon, but hey, we made a release today, so we're ahead of the game. We've created a brand new telemetry data from our computation data in Eris with the Eris backend of multi-machine rendering, which we provide as a visual overlay to the renderer so that we can inspect, optimize, and debug multi-machine rendering, which can be otherwise quite difficult to do. And I'm going to cover that tomorrow in a session that's geared specifically around Eris. What's coming up in the future? We're keen to iterate on our XPU mode. So we do have an XPU mode where we run, actually, we utilize the graphics card as a GPU solution. So we use it as a coprocessor. We don't run the entire render on the GPU. We use it as a coprocessor to the CPU rendering. We're keen to iterate on that and pile even more work there by processing primary arrays in that mode. Right now, our current implementation processes just occlusion or shadow rays. Of course, also implement new features to help our productions push the look in all of their new upcoming shows. We've also accepted our first individual contributions, and we look forward to many more. Please send us your contributor license agreement if you wish to contribute. Speaking of which, I mentioned Intel developed the open source open image denoise library for CPU and GPU, and we'd like to thank them for contributing that integration to MoonRay, and we're pleased to see it as part of its capabilities. We found that the 4004 Morehouse asset that Intel also open sourced earlier this year to be useful to validate our Hydra implementation and compliance. And in the reel that we just watched, we rendered that asset on one host with no denoising, one host with denoising, 32 hosts with no denoising, and 32 hosts with denoising. Additionally, in collaboration with the Metal Ecosystem Engineering team at Apple, we have MoonRay up and running seamlessly on Apple Silicon with full support for XPU mode using Metal. Thanks to Apple Silicon and its large unified memory pool that both the CPU and GPU can access, we have the ability to render large assets that are difficult to render when the BVH doesn't fit in the VRAM of a discrete GPU. In other words, it's amazing to see that we can run MoonRay comfortably on a laptop. My favorite part of this video is watching the CPU core count light up at the bottom right there. Now, this is a feature production quality scene that's called A-Lab, which was kindly open sourced earlier this year by the studio Animal Logic. And here we're showing the A-Lab scene rendering at about 60% complete on a Mac. And if you notice, we are toggling the Intel's open image denoise on and off. So you see it get a little bit smooth, a little bit grainy, a little bit smooth, a little bit grainy. We're toggling the denoising on and off there. So Regarding why we chose to open source, we believe in the strength and the resilience of the open source community, and we hope that MoonRay excites the graphics community and allows the code base to grow stronger, and establish and develop partnerships with educational institutions, companies, and individuals. To be transparent, we do think MoonRay is a great tool in the arsenal for those who will adopt it, but there are selfish reasons for us to provide this technology to the open source community. We want to use MoonRay with partner studios, but there was no way for artists to learn MoonRay except inside of our studio. We absolutely want this effort to extend MoonRay's reach. We want access to the smart, creative folks in the open source community. And it's already proved a success. I mentioned that Intel has provided integration with their machine learning denoiser that's also open source, and we partnered with Apple to get it running there. And I know that DreamWorks itself is entirely a Linux shop. This is a conference hosted by a Linux company. But yes, one last call out for contributors. We don't feel like we need to own the entirety of MoonRay, its plugins, nor its variants. Honestly, we personally are not going to benefit if it gets onto Windows, but we think the community at large could, and we feel like others can and should be experts in many diverse areas of MoonRay. So this is a transparent and fairly materialistic view of some of the reasons why we want to open source this technology. However, we have other motivations as well. And for this next section, I want to show off some of the stuff we've done with MoonRay that showcase its application outside of feature animation. And let's continue on. There we go. First up is in the 3D printing space, where we collaborated with HP to integrate a specialized shading model, which allows us to render and visualize a 3D printed object before incurring the cost of doing the actual printing. Here's a picture of the scanner that HP has. The 3D printed exemplars, or 6 sides of a cube, are laid out on the scanning bed and scanned, and this example shows us scanning the normals. The 36 resulting textures, 6 sides times 6 types of data, are then projected onto a 3D model in MoonRay. This describes the AXF shading model developed by Xrite and used to model 3D printed objects. Here's a contrived example of what the resulting scans look like visualized as texture maps and how each plug into the shading model on the previous slide. Each scanned image is used as a texture map to derive the parameters of the AXF material model. We use a technique called triplanar projection to apply the scanned textures to the 3D model, resulting in a MoonRay render of our widget model using the AXF material, which was fed by those real scans from the 3D printed exemplars to acquire the texture data. However, the 3D printing process has some limited resolution, so here we modified our widget model to show what that would look like. The scale of the stair stepping is accurate to their printing resolution. Finally, we show the actual 3D printed model compared to the render. Oh, I got more. Next up is in the VR space, where we've integrated vNova's Presence Z SDK as a VR camera in MoonRay. Presence Z renders a box from which all points of view are traced to the outer volume of the box and generates a point cloud, thus allowing 6 degrees of movement within that box, so that a person can look around, tilt their head, and look behind objects in the scene. In other words, it's not a flat painting on a cylinder that one is standing inside of. In this video capture of our VR session, we've rendered 5 boxes within the scene. Again, it's the A-Lab scene. It was open sourced earlier this year by the studio Animal Logic. And with 5 VR boxes, we allow greater horizontal movement around the room to inspect all the gadgets. In this VR session, we'll step outside of the boxes, and the viewer can then see them all stacked horizontal next to each other. And I'm going to just go forward a little bit here so we can see that. And there you see we're stacking boxes next to each other that we've rendered in the scene. Next up is I'm going to show a test that we did of real-time motion capture with MoonRay and Eris. So we did this test in early 2016 on our motion capture stage. The configuration we set up is a good example for the Eris framework. The test is showing real-time rendering with MoonRay. The front-end application is Autodesk Motion Builder on the left, which receives live mocap data and streams to the Eris backend. We dedicated 18 Eris hosts to the test, each with InfiniBand connections. The total core count was 40 cores per host times 18 hosts, or 720 cores. The CPU on the host was a 2.8 gigahertz Intel Xeon. The Eris backend consisted of 3 parts: 1 host for deformation, 2 hosts for wind and collision simulation, and 12 to 16 hosts for rendering with MoonRay. Our frame budget was 41 milliseconds to render in order to achieve 24 frames a second. Within this 41 milliseconds, we needed to finish 2 phases for rendering. First, the render prep phase, which reads the scene data and the delta changes, and secondly, the MCRT phase, which actually calculates the ray intersections. Render prep took about 5 milliseconds, or 10% of our budget, and the MCRT phase took around 35 milliseconds, or 90% of our budget. And as you can see, the latency was a couple of frames from the incoming live mocap data to the final render, but the overall throughput was 12 to 24 frames per second, and so we achieved our goal. We consider this to be quite impressive for CPU-based rendering back in 2016. Let's look at a multi-context workflow. What do I mean by a multi-context workflow? Well, one example is that a look development artist can benefit from the ability to render multiple takes of the same asset, allowing them to test their work under different lighting conditions simultaneously to make sure that their carefully crafted materials hold up under any lighting condition. In this video example, we're showing asset development under multiple lighting conditions in a single session using Eris. It took a few seconds to transfer the scene and asset data to the back end, and distribute it to the nodes. And once we got going, we get fast delta updates as we pan the camera around and change radiance values. The artist can see and manipulate the asset under 4 lighting conditions at once: daylight, overcast, dusk, and night. And I believe that the van asset here is called Mr. Licky. Yeah. So to close on our motivation to open source, I mentioned some of the standard things that benefit most open source projects, but I do want to touch on something more basic in having that desire to share, and that is a sense of accomplishment. We are tool builders, and one of the neatest things about this job is not just building the tool itself, but seeing it put to use, and particularly seeing it put to use in ways we never dreamed of. Artists do amazing work, and we often find ourselves surprised and delighted in the ambitious look of our films. It's stunning to think that they made something with such beautiful imagery and emotions using tools that we built. We take pride in seeing what people do with our tools in the graphics community. Why not share and expand that? After all, where does our sense of accomplishment come from? Watching people make something amazing from that which you've given, instructed, or instilled in them. And we are in a continuous cycle of being learners and being teachers. Open source, we feel, is a virtuous circle. I watched the legendary skateboarder Rodney Mullen, inventor of the ollie and many other street skating tricks, give a TED Talk comparing the skateboarding community to the open source community. He describes that the unique environment skaters play in drive the creation of new tricks, fostering prolific ingenuity purely for passion's sake. And I'd like to quote him now. Quote, "There is an intrinsic value to creating something for the sake of creating it. Better than that, there is this beauty of dropping it into a community of your own making and seeing it dispersed and seeing younger, more talented, just different talent, taking it to levels you could never imagine, because that lives on." We wholeheartedly agree. I'd like now to share some final thoughts. In development for 10 years, and the last 6 years are its active life as the production renderer at DreamWorks, our key focus since the beginning has been performance, and production features have ramped up. The challenge is to maintain a high level of performance while we continue to grow this feature set. MoonRay has achieved a strong foundation for feature animation production at DreamWorks, and we are excited to see where it goes outside the studio and even within other industries in academia. I'd like to thank the MoonRay and Eris teams at DreamWorks for being such awesome folks to work with and almost as pretty as everybody here in this room. I'd also want to give a big thank you to Canonical for hosting the event and allowing me to introduce MoonRay and our journey to open source with you all. I'm going to apologize to my team. You guys are just as pretty. And especially thank you all for your time and attention. We're excited to share in this technology and eager to get talking even more about MoonRay with you all. Thank you.
Very good job. Thank you, Vince. So I think we're up at time, actually. And we have 4 minutes. Would you like to take some questions?
I'll take any questions.
Fantastic. Raise your hand if you have a question. Back there. We have a mic headed towards you.
Were there any major concerns or blockers from executives and other stakeholders when you were trying to open source? And if so, how did you overcome those?
Major concerns or blockers? Not particularly. I think overall it was just a convincing argument that we made over time to say, hey, this technology is not the secret to our movies. We make movies. Secret to our movies is our artistry and the stories that we tell. And this technology deserves to be out there in the world. We've invested many millions of dollars, and this technology's been under development by a team for many years now. We've invested many millions of dollars in it, and why keep it hidden behind doors if it's not, this is not, we're not out there selling the product, right? Other people do that. We're out there to make movies. And so, our executives, they listen. Might take them a while, but they listen.
Awesome. Thank you.
Do you know off the top of your head what license it was released under, and how much consideration did you give to the license when you're open sourcing it?
Yeah, we gave a lot of consideration to it, and it's Apache 2.0. Feel free to use it. Make a company, Make a company that does, I don't know, back-end rendering services on the cloud or something.
Do you think the future of film rendering is still CPU or maybe specialized hardware or GPU rendering?
Well, GPU has obviously got everybody's attention. It's very, very fast. It's nowhere close to being, the memory capabilities aren't anywhere close to being able to do the kind of features that we do. Just our scenes are far too large.
It's just a memory issue. It's not like compute problem with the algorithms.
Not really a compute problem with the algorithms, more the memory.
Thanks.
If you scale up a huge GPU render farm, though, I'm sure you can get it done at a larger expense, for sure.
So you talked about porting to CMake and everything. Most graphics people that I know don't know how to build software. Is there any plans to engage with the community to get it packaged properly in an archive of Ubuntu or Debian, or into a snap package, or into a Flatpak?
I would love it. Come talk to me. Our team internally, we're highly focused on our own productions, and our own productions do not need that. So it would be a very long time before we would do that ourselves. Exactly.
We just extend your user base. That's right. Time for one more question.
So you talked about convincing the executives of open sourcing it. Do they see this project, the open sourcing part, do they see that as like a testing ground? And if so, what metrics do they have to see whether or not this open sourcing was successful?
Well, they do see it as a little bit of a like, hey, look at this. Look how well the technology did. We got a lot of great feedback. We got a lot of people who forked the code right away, a lot of people who favorited us on GitHub. All of these things are looked at. We have analytics on our page, so we know roughly how many users are coming in. It's still quite a lot. So yeah, I think all of these things are quite positive for our rollout.
Thank you, Randy, so much.
Thank you very much. I mentioned if anybody wants to stick around, the very first thing that we ever rendered with MoonRay was a short called Bilby, and we've got Bilby here today, and we're going to show it. Feel free to stick around, or you can leave. It's not going to hurt any feelings here. But I would like to show that off. I think it's nice to see. And with that, get right in.
Thank you very much. That was amazing.